Hi, welcome to Rad Exchange. My name is Craig Dial, and I'm going to be talking about maximizing your cone beam CT. Earlier in the first part of the series, we talked about image resolution for calibration. Make sure that you listen to that video. Today, we're going to talk about the signal and noise ratio that can directly affect your image resolution on your cone beam CT. Signal to noise ratio is a common term in electronics performance, but it can apply to any electronic processes. So signal is good information and noise would be bad information. So if you like a song that's playing on the radio, you turn up the song, you get more signal, that's good information. You go into a tunnel and it gets staticky, that's noise, which is bad information. So in our scans, we like to have a high signal and a low noise relationship. In cone beam CT, one of the ways to get signal is to adjust the frame rate of how often the picture is taken. The more frames, the more signal, the more images. So the computer, the cone beam, takes samples around the patient's anatomy and it collects frames, sometimes between 100 and 600 frames, depending on your machine. The more frames, the more signal, the more good information. Also, it's the frame rate. So how often does your machine capture the information? The sensors themselves might capture at a frame rate per second of maybe 15 frame rates, 32 frame rates, or other. So the more frames is the more data, which is better signal. So the more signal, the quality of the image is improving. And the frequency of how these machines are taking the images can also vary. So a 20-second scan of a 15 frame rate per second equals 300 total frames. But another scanner that has a faster capture rate might do 32 frame rates per second, 8.9 per second scan, still 300 total frames. The accumulated dose is the same, but the frame rate is captured at a different frame rate. So we're actually able to get the same data with less time. But that's sample frequency. How frequent does the images get captured? That's all with good signal. Noise, on the other hand, is the stuff we don't want, the bad stuff. And we want to get rid of or eliminate or reduce noise as much as possible. So voltage is introduced into the machine can vary. If you work or have an office that might be in an old home or an old house, and the variation of the power can adjust, brownouts and things like that, you want to isolate yourself from those types of inflexible electronic noises. So if you have inconsistent power in your office, I highly recommend using a voltage regulator attached to your machine so you get clean power and less noise into your machine. Scatter also is something that we have that introduces noise. The patient's own dense structures, a large person, bone mass, metal objects, even a large field of view, all introduced noise or scatter into the X-ray. If you remember back in the books of the days of reading about X-ray, when the X-ray hits a hard, dense structure, it often will bounce off and record onto the sensor and get fog or noise into the sensor. So sometimes there's things that are just affecting the image quality by the size of the patient or the dense structure within their cells. I'm going to give you an example for a panoramic that was taken 2D pano, and you can see those white lines that are vertical on the X-ray. That's a dense structure. And I want you to think about that for a minute and figure out what you think that dense structure might be on a regular 2D pano. And what it ended up being is a patient with tightly braided hair that was wet. That's a dense structure that can affect the image quality. So as you can see, dense structures can introduce noise into our scan, whether it be 2D or 3D. So you might have done an excellent quality scan on a patient that happens to be large bone mass and large tissue mass. The patient didn't move, but the scan is noisy. And the scan's noisy due to the limitations of what we have to work with our CT scanners. Large bone mass equals dense structures equals noise introduced into the scan. And if we think about the opposite might be true, you ever notice that you have a small bone mass patient, edentulous case, the image quality is excellent because the energy goes through the patient, records onto the sensor, and we get good detail with those kinds of cases. The same thing goes with small children. You get small bone mass, and therefore you can really tone down or tune down your X-ray machine for a lower dose scan for these types of patients because it doesn't take that much energy to record onto the sensor. And dense object matter, such as metallic objects, what we talked about, that introduces noise into your scan. You get scatter onto the scan because of the noise. And there's nothing we can do about these things. This is dense object matter scanning, and scatter, that's just the fact of the limitations of cone beam as of it is right now. And metallic objects such as earrings, as you can see, will scatter the X-ray beam. Even if it's out of the area of interest, it scatters across the entire region of that plane. So you see the beam hardening is another word for this. As you can see the shadow of the beam of the earrings in that field of view. Noise can be introduced with beam hardening through implants. And sometimes you want to see the between the implants how much bone the patient has, and it's very difficult to see due to this beam hardening artifact of the noise that's introduced into our scanner. So it's the limitations as of now for cone beam CT. Earrings, even though the earring is way back on the face, you can see the waves across all of the teeth. It makes the teeth look irregular, and there might be a feeling like there's something going on in the teeth, but it's not. It's the noise introduced into the scan. So when we take our scans, try to get everything removed as much as possible. Earrings, nose rings, tongue rings, everything that you can to get rid of that noise. There are times when you can't always remove the earrings and the jewelry, and that's what you have to deal with. So the point being is do the best you can about getting rid of as much metal artifacts as you can. The sensors themselves, depending on the manufacturer, can introduce noise into the scanner. By changing the signal from digital to analog and back to digital, some of the sensors can have an effect on image quality, such as the image intensifiers. Although these sensors are improving to isolate the electronic noise. But what happens with the image intensifiers is the X-ray goes through the patient, records onto a CRT, it gets focused onto an optical, and then sent down to a CCD chip. And this transition from signal back and forth to digital and to analog introduces noise into a scan. Here's an example of a scan that has a lot of noise in it due to the sensor. This is the limiting factor of this scanner. This is a good image. This is the best image that this scanner can do. And the purpose of the imaging study was to evaluate the lower left mandible implant on site number 18. The radiologist says they can't see the left mandibular canal and the alveolar ridge as well enough to determine what's going on. So they asked me to take a look at it, and I just looked at the hard data behind the CT scan and found out this is a original 8-bit CMT scanner. So it has a limited quality X-ray picture. And so it's just the noise is introduced into the scan because that's just what the sensor is giving us. And I realize that sensors and scanners are expensive to replace. They're expensive to maintain. Sometimes manufacturers discontinue models as part of the evolution of cone beam, where we must upgrade to the next generations in order to stay current and keep our machines operational and up to the standards that we need. But that's all I'm going to say about signal and noise ratio. Just make sure that you understand the basic principles. Look for future videos on other parts for image resolution. Thank you so much.